In today's lesson, we are going to be looking at distance and time graphs. So this is going to be an extension on the kind of investigation that we did the other day where we were looking at how movement could create graphs. So now we're going to be looking at them a little bit more specifically. But just to recall a bit, by looking at a distance time graph, we can determine the general speed an object is moving by. And if we were to look at this graph here, could we tell what some of the speeds are? So for example, you might say a flat line, no speed or movement. What would a steep line indicate? Or what would a shallow line indicate in terms of speed? Well, a steep line would mean moving fast, and a shallow line would be moving slow. So if you don't quite remember that, again, please go back and look over the previous lesson, but this is what we looked at when we used the CBRs or the motion sensors. The video for the previous lesson looks at a Desmos investigation that kind of displays that as well. So for speed, that's what we're going to be looking at today. And the formula for speed is velocity is equal to distance divided by time. Right? So if you haven't taken that yet in science, velocity is distance over time. Right? And we can determine the distance traveled of a segment by looking at it could be a couple things. It could be the change in y, right? You might also say the rise of the graph. And we can determine the time of a segment by looking at the change in x or the run of a segment. So how far horizontally do we move? And then when we have a graph of distance and time, apologize about that. When we have a graph looking at distance and time, the speed is also known as the slope, or you could say the multiplier, or more specific probably, because we're not really dealing with a pattern anymore, might say the rate of change. But the multiplier is another common term for that value, so you could use that as well. It's just multiplier is more applicable when we're dealing with maybe word problems or visual patterns. So in example 1, Chris runs each day as part of his exercise routine. The graph shows his distance from his home as he runs his route. So what we want to do is for each section, we want to figure out the direction he's going, the distance, and the time, and then calculate the rate of change or the speed. So in section AB, the first section here, the direction from his home, he's moving away, right? Using a line that's a positive line means he's moving away. The distance traveled is 200 meters, and the time is 5 minutes. So in this case, his speed is 200, or distance divided by time. So 200 divided by 5, which equals 40 meters per minute. So we want to make sure we're including the units in this case because we want to make sure we're specific because the units can make a difference, right, in terms of speed. So we want to be clear on what our units are. From B to C, right, so we can see we use a different color for this one, from B to C. So going from here to here. Okay, let's just color in the line to make it a little bit easier. From B to C, he's again moving away because the line is going up, the distance is increasing. The distance in this case, even though it ends at 1,000, we have to remember where we started, right? Just like when we're doing rise over run or slope or looking at points, we want to find the slope. We want to figure out what was the distance traveled from where he started. In this case, he only traveled 800 meters because section C starts at 200 meters. So it starts at this level and ends here. So you've traveled 800 meters in 5 minutes. To calculate the speed, 800 divided by 5, we get 160 meters per minute. So he's really sprinting. CD, the next segment, will make sense that he's slowing down. He just sprinted for 5 minutes. So CD, again, the line is increasing, so he's moving away. The distance traveled, in this case, from 100 or 1,000 to 1,400. He traveled 400 meters in 5 minutes. Again, so the speed or the slope or the rate of change is 400 divided by 5. Which equals 80 meters per minute. So he's slowing down. And again, we can see that based off of the line, right? It's less steep than the previous segment, so it should be smaller or have a smaller slope than 160. For DE, this segment, this was one of the unique ones. So his direction, he's just not moving. You could put stopped as well, but there is no change. There's no direction. He's not going away. He's not going towards. He's just not moving. The distance traveled is 0, and the time for the segment is 5 minutes. So 0 divided by 5 equals 0 meters per minute, which makes sense because he's not moving. He's stopped. So when he's stopped, his speed is 0. And then lastly, the last segment, EF. So EF, we are going from 1,400 to 0. So in this case, he's moving towards. The line is coming down or it's decreasing. So he's moving towards home. The distance traveled is 1,400 meters. And the time is 5 minutes. 1,400 divided by 5 is 280 meters per minute. So which is incredibly fast. So maybe he got a ride from someone or he jumped on a bike or who knows what the case is. But that was his speed for the final segment. So again, essentially all we're doing is we're finding the slope of each line segment. If you prefer to think of it as rise over run, you can. It just might be a little bit easier sometimes to refer to it as the distance traveled in that segment and how long did that segment last. So just different terms, but essentially we're still doing the same thing. So how long did it take Chris to run his route? So if we go back, his entire route is the entire trip away and then back. So we start at A or at 0 and we end at F or 25. So in this case, it took 25 minutes for him to run his route. How long did he stop for? Well, we can go back to that segment. You can see it at the top here, DE, where he wasn't moving. He was stopped for 5 minutes. How long would the trip have been if he had not stopped? Well, take the 25 minus the 5 minutes. His trip would have been 20 minutes long. Can you have a negative speed? And what does negative speed symbolize in a distance time graph? Well, we only have one negative speed, and actually, that would be E. We kind of made a mistake. EF, we go from 1,400 to 0, so actually, that's a distance traveled of negative 1,400 meters. So negative 1,400 divided by 5 is negative 280, which is fine. That's the slope. But now it comes back to this question. Can we have a negative speed? And the answer is no. You can't have a negative speed. But we've just shown that we do have one. We calculated our speed from our graph. We have a negative speed. We clearly know we can't have a negative speed, right? If you look at a speedometer, it's always positive. It goes from 0 to, 240, right, kilometers per hour. There's no negative numbers there. So what does our negative speed symbolize? So the speed is actually just the positive value, the 280 meters per minute. The negative means moving towards. So the negative slope refers to the direction of the person running, or in this case, Chris running. So the negative means he's running towards home. The positive slopes meant he was running away. But when we're looking at speed, we would refer to just the 280, even though we do have a negative, because we'd understand that the negative only refers to the direction. Looking at example 2, we have 2 runners running. Who got a head start? Well, if we look at them, runner B got a head start because they started closer. And we can see that by this y-intercept. This y-intercept is 30. Runner A was at 40. So runner B started closer. Who is the faster runner? How much faster were they? Well, we could go through, look at runner A, right? We could say, okay, their distance was 40, negative 40 over 4. We don't really have any units in this case, but negative 40 over 4 is negative 10. Again, that's just referring, the negative is just referring to the slope, to the direction. Runner B, they went from 30 to 10, so negative 20 over 4, which is negative 5. So in this case, runner A is faster by 5, we'll say units, because we don't know the specific values. So the runner A is faster by 5 units. Whether it's 5 kilometers an hour, 5 meters per minute, whatever the case is. Who won the race and how do we know? Well, I would say that runner A won the race. And how do we know? They reached 0 first. So their distance towards, you could say, the start or the finish, right? So this was the finish. This was the start. So they reached 0 first, or they reached the finish line first. Where do the two lines cross? What does this point mean? Well, they cross at the point 220. And what does this point mean? Well, at this point, they're at the same spot. So both runners at the same spot at the same time. So both runners are at the same spot at the same time, referring to this point here, 220. We'll be looking at that further in a different lesson, but it is called the point of intersection. So at this point, the runners are at the same spot at the same time, right? So they meet each other, they cross each other, whatever you want to consider. But they're at the same spot at the same time. Or you prefer that to meeting or crossing, one overtakes the other, however you want to word it based on the scenario. So the main thing from this lesson is just, again, understanding how the movement or how movement appears on graphs, especially when looking at a distance time graph, as well as looking at how can we actually calculate speed. Right? So we can calculate speed by essentially finding the slope of a line. And we've done that before. We've done that by looking at patterns, right? We've done that by looking at graphs, at lines, at equations, at tables, right? We've already done that in our previous lesson. So it's a lot of review. It's just focusing on a specific scenario, which is the distance and time graphs.